Today we're going to learn about antiderivatives. But first, why do you need them? Here we have a regular curve, and we're trying to find the area underneath the curve. Now, we've learned that you can break it up into rectangles of similar size and add up the rectangles. Well, for an antiderivative, all you need to do is have an infinite amount of rectangles and sum all those up, thereby finding the exact area under the curve. These rectangles then have a width of dx. We'll need that later. Okay, so let's start out with the most basic integral or antiderivative, and I'll use those interchangeably. They're pretty much the same thing. So we're going to start by learning a simple integral. What is the integral of x? And we put a dx on the end of every integral to denote the dx of the amount of x's we are summing up, correct? Infinity. Okay, so this integral happens to equal 1/2 x squared plus a constant. Let's try another one. Let's try the integral, or, oh gosh. Let's try the integral, or find the antiderivative of x squared. So what function can we take the derivative of for the derivative to equal x squared? Okay, so this one is 1/3 x cubed plus a constant. So we see a pattern here emerging. So a good formula to use is any x to the n, or any n to the n, dx equals 1/n plus 1 times x to the n plus 1 plus your constant. Okay? So this should work for a lot of polynomials. Now I say a lot. So let's try another example. Okay, let's try the integral of x to the -1 dx. So if we use our formula, saying that this should equal our n plus 1, x to the n plus 1 plus c, we're saying that this needs to be 1/-1 plus 1. And we can see a problem right here. This is already going to equal 0 on the bottom. Now we learned a long time ago this is not okay. So we need another formula for it. This one you actually just need to know. The answer to this antiderivative is the natural log of the absolute value of x plus c. Okay? So as you can see, there's no one set formula, no one set way to approach every integral. So really the only way to get better is to practice them. When you're given just a random integral to solve, you need a good place to start. So I'm going to show you a couple properties of integrals that can give you some direction on where to go. So the first property I'm going to show you has to do with the addition of integrals. So if you're taking the integral of two separate functions added together, that's the same as saying you're taking the integral of each function separately and adding those together. That's an addition sign. This may not mean a whole lot to you right now, but believe me, this is a very helpful way to solve the polynomial types. Really, this is one of the first things to go to once you're seeing a long, drawn-out integral. See when you can split it up and work with it in separate chunks. Note that you can do subtraction the same way. Exact same. So another thing, another thing to note is that if you have the integral, and I should just stay over here, of some constant times a function that equals the constant times the integral of the function. Or this is going to be a times the antiderivative of the function f of x dx. Okay. Also important to note that where you have the chain rule and the product rule and the quotient rule that work all the time for your derivatives, no such thing exists for antiderivatives. So really it's all about practicing new things, all these new techniques, all these methods that you will learn in the coming weeks. So I'm just going to show you a couple more examples just for you to reference, such as with the trig functions. So if you try to find the antiderivative of cosine of x dx, again you're asking what function, when you take the derivative of it, equals cosine of x. That's going to be not an integral. That's just going to equal sine of x plus your constant. Now you see how this works. If you take the derivative of sine, you get cosine. Take the antiderivative of cosine, you get sine. That's how it works. Another one. The integral of 1 over 1 plus x squared dx is actually equal to tangent to the minus 1, or the arctangent of x plus constant. This is one of those that you probably should memorize. So let's try another example. The integral of cosine squared x dx, don't forget dx, actually is equal to 1/2 of x plus 1/4 of the sine of 2x plus c. What? Here's how we got that. To solve this integral, you have to actually use a trig identity. So we know that cosine squared of x is also equal to 1/2 times 1 plus the cosine of 2x. Okay? So your integral then is going to look like this. So again, we're taking the integral of cosine squared x dx. Now we're just going to substitute all of this in for your cosine squared x. So this means the integral of the 1/2 times 1 plus cosine 2x dx. Alright. Now, there's a couple different ways you can do this. Right now, I'm going to take the 1/2 and put it on the outside of the integral, just like I showed you a little before with the a. So here a equals 1/2, and we are allowed to put it outside and just rewrite this whole thing. 1 plus cosine 2x dx. Alright. Now we can use another of our properties. I'm sorry, this is awful. The additive property that we used. So we're going to take this 1/2 integral and apply it to both the 1 and the cosine portion of this. Alright? So it's going to look like 1/2 of the integral of 1 dx plus 1/2 of the integral of cosine of 2x dx. Okay. Now we're going to solve. And I'm just going to bring it up here. One half the cosine, or 1/2 the integral, excuse me, of 1 dx is just simply 1/2 x. Do you see where we got that? Because when you take the derivative of 1/2 x, what do you have? 1/2. All right. Now we're still going to add it to this integral right here. 1/2 integral of cosine 2x dx. So I showed earlier where the integral of, or the antiderivative, same thing, of cosine is sine. Well, that is still true, except for you. It's not that easy when you have that 2x in there because of the chain rule. So again, we are referring to derivatives here, referencing back to the derivative that will give you this function. We're going to say that this portion equals 1/4 sine of 2x plus c. Okay? Why is this? Well, prove it to yourself that the derivative of this is equal to this. Because when you take the chain rule and you multiply this whole thing by 2, this will become 1/2, which appears here. Okay? So again, the answer to where we started out here with cosine squared is this whole thing, which is 1/2 x plus 1/4 sine 2x plus c. That's going to be more involved ones. So now let's work on actually applying these integrals to your graphs. So let's say we're given a graph of x squared. So it looks something like this. And you're wanting to find the area under the curve between x equals 1 and x equals 3. That's 3. So we're talking about the area from here to here. All right, how does this look in integral form, in antiderivative form? This is actually going to be your integral from 1 to 3, okay, of x squared dx. Again, this is f of x equals x squared. So let's back up. This 1 and 3 are your x coordinates, the bounds of your antiderivative. So what we're actually going to end up doing is finding the area in between these two bounds. All right? So we learned this earlier. This integral, the antiderivative of x squared is 1/3 x to the third plus c. Now, since we have bounds on our integrand, so this is integrand, we actually denote this by putting a bar and 1 and 3, just as they appear here, meaning we've taken the integral, but now we're going to apply our endpoints. All right? So what this means is that we're going to take the formula with x equal to 3 minus the formula with x equal to 1. All right, so it's going to look like this. 1/3 of 3 cubed and plus c, all of that minus all of 1/3 of 1 cubed plus c. Now something we can see right off the bat is even though these don't look very similar, these are equal, both c's, and since you're minusing, they're going to cancel out. So we can go ahead and do that before anything. Now let's go on and simplify our equation here. So 3 cubed is 9. 9 divided by 3 cubed is 27. 27 divided by 3 is 9. So this is all equal to 9. Minus 1 cubed is 1. Divided by 3 is 1/3. That's all it is. We just found that the area under x squared between x equals 1 and x equals 3 is equal to 8 2/3. Okay, so to wrap things up, we're going to do an example where we bring everything we've learned together. So what we're going to do is find the area under this straight line. This line happens to have the formula f of x is equal to h over b. That's an h. X. So, straight line. This, wow, okay. So the x coordinate is the letter number b, and the y coordinate is h. Alright, so again, finding that area. So in integral form, this is what it's going to look like. We're going to find the antiderivative of h over b x dx between the bounds of 0, or 0, and b. These are x coordinates. So first, the antiderivative of this portion is going to be, as we've learned, 1/2 times h over b times x squared plus your constant. Now, what you probably should get in the habit of is when you see these limits on the integrand, you don't need this constant because it's always going to cancel out. Okay? So, we're not done yet because we have limits on our integrand. From here, we put our limits into the x and subtract. Start with the top one. So it's going to look like 1/2 h over b, b squared minus 0 squared. Now you see how you can do it this way, or write them all out and subtract the entire thing. Both work just the same. So obviously the 0 squared is 0. So we can write this as 1/2 h over b squared. Now this can simplify even further by canceling out these b's. And we're left with a formula. 1/2 HB. In other words, your area of your triangle is equal to 1/2 times your base times your height.